Okay, anyone remember what this symbol was for? Capacitor. So what was this symbol for? Battery. And why do we have a big line or a short line and a long line? Yeah, it was your positive and negative sides of your battery there. So as your imaginary positive charges flow through this battery, they go from low potential to high potential, from low potential energy to high potential energy as they cross. Cool. Now when we get to, let's do this again. Actually, so if I put another capacitor in this circuit, how are these two capacitors related? They're in series. So if any current that flows through one has to flow through the other. There's no alternate pathway there. So however, how are they related in this circuit? They're in parallel. We can do the same thing with resistors. The symbol for a resistor is a squiggly line like that. And so they can be arranged in series, and they can be arranged in parallel as well. And so again, here in series, any current that flows through one resistor has to flow through the other. And so they have exactly the same current flowing through them when they're in series. Cool, but when they're in parallel, they don't necessarily have to have the same current at all. So they're on alternate pathways. As the electrons as the imaginary positive charges flow from the positive terminal to the negative terminal, they have a pathway that goes through the first resistor, or they have an alternate pathway that goes through the other resistor. Since they're on separate pathways, they don't have to have the same current at all. So what we'll find out is that when they are parallel, so what is the same? It's not the current, it's the potential drop is going to be the same across either one of them. So, but even though the potential drop is the same, we'll find out then that the current prefers the path of least resistance. It's kind of where that phrase comes from in this case. So whichever one of these has a lower resistance, that would have a greater current. We'll find out. So, but the same potential drop. Okay, so let's look at this here. Let's look at Ohm's law. What's delta V equal to again? Cool. And if we rearrange that, what's I equal to?
Delta V over R.
Cool. So look at that for both of these for just a second. So in this case, how is I related to R? Inversely proportional. And how is I related to delta V again? Directly proportional. So if these two resistors have the same current, then the value of delta V over R is the same for both, right? Now, do these have to have the same R value? No, they're just two random resistors. And so what you find out is that the one with the smaller resistance would have to what if the I's come out the same? No, so in this case, if R is smaller, then delta V needs to be smaller as well to get the same I value. So in series, the smaller resistor has the smaller potential drop. Cool. Now, for the parallel situation, it's not the I's that are the same, it's the delta V's that are the same. And so Ohm's law proper is the one we want to look at here. And so if the delta V's are the same, then the one with the larger the larger R, what's going to have to be true about his I to get the same delta V? Got to be the smaller I. And so that's kind of where those relationships talked about. We talked about when they're in parallel, the one with the larger resistance is going to have the smaller current. The current prefers the path of less resistance. The one with the smaller R will have more current. So it turns out these add exactly the opposite way as we did capacitors. So if you recall, two capacitors in series, how do we add them? The reciprocals. What about when they're in parallel? Just add them directly. It is exactly the opposite for the resistors, and it's just down to the relationships here. So, but here for resistors in series, your equivalent resistance between the two is just equal to R1 plus R2 plus however many resistors you have. They add directly. It's in parallel that they're going to add as reciprocals. Ooh, let's not make it. It's 1 over the equivalent resistance. Cool, if you recall, there's a little trick for this though. As long as you only have two resistors, when you add them as reciprocals, again, you can just simply multiply them and then divide by the sum of them. So the product over the sum. Again, it only works when you have two of them. So let's explore this a little more here. Let's get rid of these capacitors now. So let's say I've got two resistors here. What would be the equivalent resistance of this circuit? 6 ohms. You just simply add them straight up together. So now what if I have the same two resistors but hooked up in parallel? What would be the equivalent resistance of the circuit now? 1 over 2 plus 1 over 4 would be 1 over the equivalent resistance, but so it would be 8/6 ohms. So if you notice, in series, how does the equivalent resistance compare to the individual resistances? It's always bigger. But here, how does the equivalent resistance compare to the individual resistors' resistances? It's smaller. So it always works that way. One thing to kind of take away with the situation in parallel of adding reciprocals, by the way, let's just say you have a bunch of identical resistors here, and let's make them 6 ohms. So if I put two of them in parallel, these two 6 ohm resistors, what would be the equivalent resistance? Well, it'll be 6 times 6 over 6 plus 6, right? Which gets you what? 3 ohms. Turns out if you have two identical resistors in parallel, the equivalent resistance will be exactly half of either value. Okay, well, let's keep going with this. Let's put another 6 ohm resistor on there. Now there's no short little trick, right? Well, except there is, but we'll have to derive it in the end. So 6 ohms, 6 ohms, 6 ohms all in parallel. What is the equivalent resistance? What's 1/6 plus 1/6 plus 1/6? 3/6, which is a half, but then flip it back over to get the equivalent resistance, and what do you get? Oh, can you? So if with two of them on there that are identical, you just cut it in half, what do you do with three of them? Take a third of it. But again, when's the only time this is going to work? If all the resistors have the same resistance. Cool, but a short little trick because that's a pretty common scenario.
Well, I mean, can you just put 1 over the resistance of each one and just add in the calculator? Or?
So you can totally just add it in the calculator. One thing to note is when we did this, we got 3/6, right? Was that equal to the equivalent resistance? No, it was equal to 1 over the equivalent resistance,
so
right?
1 over that whole thing.
Right, so once you get 3 over 6, you got to flip back over to 6 over 3. So that is the most common mistake students will make here is they'll forget to flip it back at the end. So don't do that. Okay, so now we're going to get into some complex circuits here. This is technically a part of what we call DC or direct current circuits and stuff like that. I've kind of pulled it in with this lesson because we've been dealing with resistance so much. In this case, we can take a fairly complex circuit diagram like this one and we can make it simpler in steps along the way till we get one overall equivalent resistance along the way. And so in this case, how are R1 and R2 related? Oh, question, Chris. Yeah.
What is this symbol?
So this symbol right here is still battery.
Oh, okay.
Whether you see one,
Why
it might be double here because maybe it's two batteries in series hooked together. So whether you see it as a double set of lines or one set of lines, just a battery, no big deal.
So batteries in series, if you have 1.5, 2 is 3.
Yeah, batteries in series are totally additive.
But in parallel,
In parallel, it doesn't work that way with batteries. Yeah.
it's more current if they're in parallel.
So
Or, I'm sorry, I've
no,
always wondered that.
you get a greater potential difference if you put them in series. And notice, how does current relate to potential? Directly. So you actually get a greater current if you have a greater potential, which is when they're in series. Okay. So in this case, we've got this lovely 12-volt battery here. And we've got 4 resistors, and we want to ask a whole host of questions about these 4 resistors. But first thing we need to do is simplify this diagram. So how are R1 and R2 related? Parallel. And R3 and R4? Parallel. So how is R1 related to R4? So any pathway I take through R1 has to go through R4? No, well, stating the relationship at this stage would actually be very difficult. So when we simplify this diagram, we're going to look at the relationships we know for sure at this point and combine them first. We definitely know these are parallel. And these are parallel. We'll combine those first and get equivalent resistances in this case. And so we'll be able to get a couple of different equivalent resistances for each set of resistors here. So for R1 and R2, notice they're identical. What would be the equivalent resistance since they're in parallel? Good, just be simply 1 ohm. And for R3 and R4, they're not equivalent, but again, we have a trick when there's only 2 of them when you add them as reciprocals. What would be the equivalent resistance?
48 over 16 is 1/3.
48 over 16, don't forget that. Yep, so 3 ohms. Great, so 4 times 12 over 4 plus 12 is 3. Great, and we've reduced it down. Now, if we look at the equivalent resistances here, how are they related?
Series.
They're in series. Before we go there, though, if I look at this diagram here, which of these has more current?
3 ohm. No, 1 ohm. 1 ohm.
It's a trick question.
3 ohm.
They're in series, which means they have the same current. Any flow of charge going through this resistor has to go through this one as well. Cool. So in this case, though, they're going to have the same current, but which one's going to have a bigger potential drop? If delta V equals IR, and they have the same I, but the R's are definitely not the same. So where are you going to see a bigger potential drop?
The bigger, the smaller resistor.
So again, which one has the bigger I?
Yeah,
The same. Which one has the bigger R? That's going to have the bigger potential drop across the resistor. So that's the way that works in this case. So what we'll find out is that some of the potential is going to be dropped here, some of the potential is going to be dropped here. What's the potential increase at the battery? 12 volts. You'll find out this later next week, but any increase in the battery will be exactly matched by the decreases at the resistors. So we should have a net 12 volt drop combined between those two, as we'll see later. But we can take and simplify this even further now to get one overall equivalent resistance. And what is that equivalent resistance? 4 ohms. Okay, so looking at Ohm's law here, in this diagram here, I've got it down to a single resistor, or at least a single equivalent resistance. What is the current?
3.
Yeah, if you solve for I here, it's 3 amps. So let's say I told you I had a hose, and this hose, when I turn it on full blast, will pump out 10 gallons of water per minute. Cool? Well, let's say I've got a splitter on the end of this hose, and it splits it into 2 separate hoses, one big and one small. And through the big hose, I can, again, now combined, what's the flow rate going to be between both hoses at the end? 10 gallons per minute. So if I tell you one goes, through the big one, it's 8 gallons per minute. That's your flow rate. Then what would be the flow rate in the small one? 2 gallons per minute. But the water's got to go somewhere, right? And if it's flowing through this hose at 10 gallons per minute, then when it splits off, it's still got a total 10 gallons per minute. Same thing here. I've got 3 amps of current leaving my battery. If we go back to this diagram, I've got 3 amps of current leaving my battery. It flows through here and it flows through here. But now I go back to this diagram. I've got 3 amps of current flowing through my battery. It hits this junction, and part of it flows through this side, and part of it flows through this side. But how much is it going to total out to? Still 3 amps of current between the 2 sides. It can't be more or less. It's the same 3 amps that flew into that junction flows out. And we'll talk about Kirchhoff's junction rule. That's all he says really next week, but it's fairly intuitive. All right, so going back through this then, a series of questions. The first is, what is the equivalent resistance in the following circuit? We figured that out. It's 4 ohms. So that's the first question. Second question says, what is the total current in the circuit? And we figured that out as well. And what was that? 3 amps. Okay, now we're going to start picking on individual resistors. So in the first one here is, what is the potential across R1? So what is the potential drop across R1? Okay, so if you notice, how does the potential drop across R1 compared to the potential drop across R2? It's the same. Okay, so let's look at this as well. So which of these would be considered the path of less resistance? They're the same. So if they have the same current flowing both here and here. And if it totals, how much current was flowing into that junction? 3 amps. Then how much are each of the currents through both sides of here? They're all 1.5 amps. Okay, so now if you know the current flowing through this resistor R1, and you know the resistance of R1, then can you get me a potential drop for R1? So 1.5 amps times 2 ohms does indeed get you 3 what? Good. Okay, another question down the tubes here. So next question is, what is the current through R4? And so here's where things are not going to be so easy. So if we look here, through R1 and R2, we're just like, well, it's equal amounts and it totals 3, so it's 1.5 amps on both sides. It's not going to be the case here. So if you notice, both these 1.5 amps join up right back at this junction. And so going down into this junction, you have 3 amps flowing in there again. But the current flowing through both sides is not going to be the same. Both sides are going to be different. Now, if we look here, when we looked at capacitors in parallel, so did they have the same charge? No, but with capacitors, we went back from a diagram like this, and we knew the total charge on some, the equivalent capacitance, and we went back here and we said, well, whichever side was bigger had more capacitance. In fact, in this case, if these were capacitors, which side would have had greater charge on it? The bigger side, right? So, and it turns out that, capacitance, the charge is directly proportional to capacitance, so bigger capacitance, bigger charge. But in our case now, delta V is the same. So, but your current is not proportional to resistance, it's inversely proportional. And so now the one with more resistance actually gets less current. Again, we said the currents can prefer the path of least resistance, and that's this branch over here. So if you notice, with capacitors, we said the charge would have been bigger on the bigger capacitance side. And in fact, if these were capacitors with, capacitances and farads, what fraction of this total charge we would have had would have been on this side? 3/4. Well, guess what's going to be true now? It's only 1/4, and 3/4 will be on the other side. So in this case, 12 ohms to 4 ohms, that's a 3-to-1 ratio, and we'll break up this 3 amps into 4 equal parts. 3/4 of that 3 amps goes on the path with less resistance, and 1/4 will go on the other side. So what is 3/4 of 4 ohms? I'm sorry, what is 3/4 of 3 amps?
So you said the more current goes on the one with
Less resistance. And so it's not directly related anymore. So this is only in this 3-to-1 ratio. So this side's 1/4 of the total if you kind of added the total between those two, but it's going to get 3/4 of the current. And what is 3/4 of 3 amps? Good, 2.25 amps. On the other side, it's going to get 1/4 of the current. And so what's 1/4 of 3 amps? Good, and it still adds up to 3 amps. Cool, so exactly opposite of what we did with capacitors. And again, the key just comes down to simply that the potential is the same. With capacitance, the charge is proportional to the capacitance, but with resistors, the current is inversely proportional to the resistance, hence the opposite relationship. Cool. Now that we've got the current going through R4 is 0.75 amps, we are asked, what is the power dissipated through R4? So in this case, what are our ways of expressing the power?
Delta VI.
Delta VI, what else? I squared R, what else?
Delta V squared over R.
Great, which one do you want to use for R4? Do we know the delta V for R4? We don't. Okay, then I probably shouldn't use one with delta V in it, so we're going to go to I squared R. So in this case, if we deal with the I squared R, I is 0.75, R is 12. What are we going to get for the power dissipated through R4 here? Awesome. So if we go back, if you guys recall, what was the potential drop across R1?
12 volts.
No, what was the potential drop across R1? We answered this question earlier. What was the potential drop across R1?
Oh, 3 volts.
It was 3 volts, right? So let me ask you a question. If that's the potential drop across R1, what's the potential drop across R2?
9 volts.
So they're in parallel. And what's true about circuit elements in parallel? Same voltage drop. So if the voltage drop across R1 is 3 volts, what's the voltage drop across R2? 3 volts. Cool. If I look then, R3 and R4 also have the same voltage drop, right? What's the voltage drop got to be?
6 total.
Well, what's the voltage increase at the battery? 12. What's the total voltage drop across this have to be? 12 as well. So what was the voltage drop here? 3. What's the voltage drop here got to be? 9. Cool. So we said a minute ago we didn't know delta V, but we kind of really could have known it pretty quickly if we wanted to.
There's 2 resistors on the top, 1 and 2 on the bottom.
Yeah.
But they're the same.
But the voltage drop for either of these is exactly the same. So if you also look back here for a second, if you look back at this part of the diagram, so recall that delta V is IR. These have the same I, but this one is 3 times the R. And if it has 3 times the R, it should have 3 times the voltage drop. And so in this case, being 3 times greater, 9 and 3 for your voltage drops adds up to 12, and it's a 3-to-1 ratio, and it totally matches what we expect. And so going back to here, with those were just equivalent resistances, it really is a 3-volt drop, either one of these, and a 9-volt drop, either one of these, for a total of 12.